Okay, so we're here today looking at a single, like kind of a strange E field scenario. Okay, and it's specifically well, you'll see in a second. So imagine I've got a positive point charge and a positive point charge. We know that the electric field should look something like this, where it comes inward and then kind of blows out to infinity. We've got this unstable point right here in the center where there's no E field, but if we kind of roll a positive point charge off the edge here, it's going to zip out to infinity, right? So what can we do about this? Well, let's think of this weird scenario, okay? And by the way, this would be like a saddle point. You'll see that in college. Anyways, let's do this kind of weird scenario. If I put directly in between, so like along a equipotential right here, if I put a negative charge and I just released it, what would happen to it? Well, if we think about this, electric field lines, their direction designates the direction a positive charge is going to move in. So this negative charge is going to move opposite in that direction. So what it's going to want to do is it's going to want to move opposite into the center. Now, some people might think that once it hits the center, it's just going to stop there. But what's really happening is, as this is moving to the center, we can think about those E field lines kind of like how we think about gravity in terms of like mass, like, you know, mechanical analog to this. Which means that as we move towards the center, we're going to be speeding up. When we hit this center point right here, we're going to be moving really fast. In fact, we're going to be moving the fastest that, you know, this negative charge has been moving at all. And because there's nothing here, well, we're not just going to stop. It's not just going to immediately, you know, do nothing. It's going to continue moving. It's going to move out. This time, though, the negative charge is moving with a field line, which it doesn't want to do. It wants to move in the opposite direction of those field lines. So what's going to happen here is we're actually going to slow down on the way out. And we're actually going to hit a point where if initially this was some distance d, now we're actually, assuming there's no friction, are going to move out to that same distance d here. This is a conservative force, this electric field. Once we get out to that point, we're going to stop. We've lost all of our velocity. We've finally lost that kinetic energy. We've come to a stop. Everything's stored in the potential energy there. And what's going to happen? Well, we're going to go back down. We're going to speed up again. We're going to be moving our fastest here, and then we're going to come out, and we're going to, once again, slow down. And then this is going to shing, 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 shing. It's going to go back and forth over and over and over again. It's going to go. And in theory, if there's no friction here, forever. We would remember this as a simple harmonic motion, often just abbreviated as SHM. So that's what's going on here in this kind of scenario, where we have this object just sliding up and down. You can actually get a very similar thing to happen, although it's kind of more finicky. If you have two positives here, if you placed a positive charge here, it would be pushed, and then pushed, and then pushed, and then pushed, and it'd go back and forth forever. Same idea with a simple harmonic motion, okay? Because I know a few students have been asking about it. Some people have asked, you know, what happens if there is friction? Well, let's think about this real quick. Normally, when we think about harmonic oscillators, and hopefully you saw this last year, normally if you have a harmonic oscillator, it's just going to follow a cosine function or a sine function if you'd like to phase shift it. But it's just going to go up and down and up and down, okay? When you have a damped harmonic oscillator, what's going to happen, well here, let's extend this a little bit. I'm going to go up and down, there you go. That's a bad tailing end, but whatever. When you have a damped harmonic oscillator, it's going to start off looking the same, but we're going to peak lower. We're going to go lower, we're going to go lower, go lower, go lower. What actually happens is we get a exponential decay here that looks kind of like that. This is some e to the negative exponent-y thing. depending on what kind of system you have here. Okay, we do have scenarios within the AP Physics C course, not the AP Physics 2 course, that look at damped oscillators to an extent. These are known as RLC circuits. LC circuits are inductors and capacitors, and those generate just an oscillation. To get a damped oscillation, you actually need the resistor component to it that acts as like friction, and it slows the oscillation down, or rather the amplitude of it. Okay, so that's just kind of a weird thing about that. Really though, what we should be focusing on is this kind of strange little example and the fact that we do see a harmonic oscillator. So with that, y'all take it easy. This right here is finished. I'll see you next time. Adios.